Hello everyone. This is section 7.2, hypothesis testing for the mean, sometimes referred to as large samples because typically n is going to be greater than or equal to 30, but it's basically based on whether or not you know sigma. And recall we did have a table back in chapter 6, and this, a flow chart I should say, and this flow chart I told you could use on the final exam. This is a different one that's in our current textbook, but I like this one the best because it just asks, do you know sigma or don't you? And if you do, as long as the population is normally distributed or n is greater than or equal to 30, we use z. And if the population is, if you don't know sigma, and as long as the population is normally distributed or n is greater than or equal to 30, we're going to use t. And because we don't know sigma, we use s in place of sigma in the formula. And so that's how to determine if we use z or t. And now look at a method of hypothesis testing that we call the p-value method. And we talked about the p-value. It means the probability that the null is true. So the p-value represents the probability of obtaining a sample statistic with a value as extreme or more extreme. So, as we had mentioned before, has to deal with the tail or the tails of the distribution based on the sample data. And since P represents pretty much, just loosely, although that's the formal definition, loosely it represents the probability HO is true. If you have a small probability, that is that P is less than or equal to alpha, the level of significance, which is the probability of committing a type 1 error, then HO is probably not true and we're going to reject it. And if we have a large probability relative to alpha, then HO is probably true and we'll fail to reject it. So we noted that here. If you got a large p-value, you're going to fail to reject HO. So there's just a couple little warm-up problems with regards to p-values. If p is 0. You might want to just set up an inequality 0.0237, and we're comparing it to, so this is the value of p, and we're comparing it to alpha, which is 0.05, and it looks like 0.0237 is less than, again that's our value of alpha, so p is less than alpha, so therefore since p is less than alpha, then we reject. And don't just say reject, make sure you always say reject HO, the null hypothesis, because the whole premise of hypothesis testing is that we're assuming that the null hypothesis HO is true. So that would be our decision for alpha being 0.05, for alpha being 0.01. Again, if you want to set up an inequality, 0.02 is greater than 0.01. Again, that's p and alpha. So now we have that p is greater than alpha. So then we fail to reject. And once again, that's our decision, and it's always made with respect to HO. So make sure you include HO there. Alright, when finding a p-value, it's basically just determined by the test statistic. And once we calculate that standardized test statistic, it's the area either in the tail, or if it's two-tailed, the area in both tails. So we basically say for left-tailed, it's the area in the left tail, for right tail, the area in the right tail, and for two-tailed, it's take twice the area in one of the tails. The tail determined by the standardized test statistic. So here's the situation, right-tailed test. So you might want to draw it. There's a distribution. Tails on the right. And the standardized test statistic was 2.33. We know z's down the middle, equaling 0. 2.33 appropriately right side test. We want the area in that tail. That's going to be our p-value. But to find that area, we first look up the left cumulative area. So this is where we go to table 4, and we should all be familiar with this, but just flash it quickly one more time. 2.33 for a z-score, there's 2.3, intersect that with 3.9901. 2.33, was that it? 2.23, sorry. 2.239871, there it is. So 2.23, I made a mistake of 2.33 down here, I apologize. So that's 2.23, and we look that up, and again, 0.9871. But the p-value, since it's the area in the right tail, is the complement of that, so 1 minus 0.9871. Or 0.0129. So now compare that to alpha. If you want to literally show the comparison, there's p, 0.0129, here's alpha, 0.10, and that's p is less than alpha. So since p is less than or equal to alpha, then we reject the null hypothesis HO. Alright, here's an example with a two-tailed test. So you're going to want to draw your distribution, and z's down the middle equals 0 again. Negative 1.20 is our test statistic somewhere on the left. Negative 1.20. Well, we got two tails, so we assume we have a symmetrical value of z there. Shade in the two tails. First off, the area to the left, you look this up in table 4 again, and you find 0.1151. But because it's a two-tailed test, the area here is 0.1151. I suppose you could just add the two areas, but typically what we do is we say that the p-value is twice the area in that one tail. And so that gives us 0.2302, and now we compare it to alpha. So 0.2302 is p, here's alpha, 0.05, p is much greater. So that means when p is greater than alpha, that means you got a pretty good probability of success that HO is true. So then we say we fail to reject HO, because HO is probably going to be true. But we don't know for sure, because we're never proving anything. We're just using these sample statistics to draw conclusions. Alright, on the next page we're going to see an actual full-blown test. So, just a reminder of the flow chart. When do you use, okay, it's a test for the population mean, and we know sigma, and either population is normally distributed or n greater than or equal to 30. Then we're going to use the z-test, or the normal distribution. And it could be either, there's this p-value method, and then in the second part of this section, we're going to look at the critical value method. But for each method, here's our standardized test statistic. Okay, and we've seen that formula before. That was the same formula that we used when we used the central limit theorem. And it is on your formula sheet. Here's your formula sheet. And you can see it's right there, and tells you the conditions for using it as well with regards to sigma and such. And we call that denominator the standard error recall. But here's the 5-step procedure. First step, state hypotheses, identify the claim. So we did that in section 7.1. Calculate the standardized test statistics, so we'll be using this formula. And we'll find the p-value like we just did. Then we'll make our decision to either reject or fail to reject, like we just did. And then state our conclusion like we did in section 7.1. Okay, so here's our first example of the 5-step hypothesis testing procedure. And on your final exam, again, I'm providing you with that cheat sheet. We already mentioned the flow chart. That's at the bottom. We already mentioned this table. I don't think I showed you the table, but there's the table for how to rate your conclusion based on what the claim is and whether or not you're rejecting HO and failing to reject HO. But also note that I have the procedures for both the p-value method and the critical value method on this little handout that again you could use on the final exam. And so you can see the 5 steps, and we'll go over them. We're going to be doing many of these, so even though you'll probably end up memorizing the steps. Oh, and when you do it in my math lab, it's probably good to go through these 5 steps and then answer the questions. Sometimes my math lab doesn't use exactly the steps that we're using. They might use 7 steps, and they're doing the same thing, but it just might look a little different. So it might be good practice just to do what we're doing and then go back when you're finished and answer the questions in my math lab. Alright, so off to the side, I'm going to rate the given data. And to peruse the problem, talking about a pain reliever. And they say the relief from headache is in less than 10 minutes. That's going to be their claim. Less than. To test the claim, they have 35 individuals. So that's the value of n, the size of our sample. And the average time from relief averages the mean was 9.25, and it's the mean of that sample of 35 individuals, so therefore x bar is 9.25. Remember the table we talked about many times. You have to make sure you understand this. That is population and a sample. If we're talking about the means and the standard deviations, mean, population, mu, sigma, standard deviation, Greek letters. For a sample, x bar is the mean, s is the standard deviation. So x bar is our sample mean. From past studies, remember past studies always means population, standard deviation, sigma is 2. And we want to use the p-value method with a level of significance of alpha equaling 0.05. Now, based on this given data, it doesn't mention anything about normal distribution, but we do know sigma. So if we're using the flow chart, do you know sigma? Yes. And then is the population normally distributed? It didn't mention that, but n is greater than or equal to 30. It is 35. So we're going to use the z distribution. So that's important, although in this section we'll be using z exclusively. We want to make sure we understand when to use z and when to use t. Alright, so the p-value method. So we've got the procedure laid out here, but it's laid out on the cheat sheet as well. And state the hypotheses, identify the claim. So the first step, the HO, the HA. Recall that HO involves a form of equality. This is strictly less than, so that's going with HA. And talking about the mean or the average time, so the mean of the population mu is less than 10 minutes, that's going to be the claim. And so therefore the null would be mu is greater than or equal to 10 minutes. Alright, so that's our first step. Second step, calculate the standardized test statistic. So Z is the formula again, x bar minus mu over sigma divided by the square root of n. So we have x bar, sample mean 9.25, it's all from the givens, right? Minus, now the population mean mu is always your hypothesized population mean. So go back for your mu, always go back to the hypotheses, and that's the population mean. So 10 in this case, all divided by sigma from the given 2 over the square root of n was 35. And so therefore we get a z-score of negative 2.22. Alright, so the third step is to get the p-value. Note that this is a left-tailed test. One tail, of course, if we're saying left-tailed. So it's a one tail left. And that's determined by the inequality in the alternative hypothesis. It's less than, so that's indicating a left-tailed test. So you're going to want to draw the distribution. And indicate a left tail. You put the z equaling 0 down the middle. And that left tail corresponds to the standardized test statistic of negative 2.22 in this case. Alright, what's in shaded is the p-value, and fortunately that's the left cumulative area, which if we look up negative 2.22 in table 4, we see 0.0132, and so 0.0132 is p. Compare that to alpha was 0.05, and p is less than alpha, and so the next step is the fourth step, which is our decision. And since p is less than or equal to alpha, then, okay, remember p is basically the probability that HO is true, small probability, less than the level of significance. So HO is probably not true, so we reject HO. And then our conclusion. And for our conclusion, you could do this intuitively, because if we're rejecting HO and HO is and HA is the claim, basically we're saying HO is bad, you can cover it up, and the claim is still good. And remember, if HA is the claim, we use the word support in our answer, so there is enough evidence to support the claim. Now you could do it intuitively. You can argue intuitively like I just did, or you could use your table. Because remember, this is part of your cheat sheet. Let me pull it out again. And it states, alright, our claim was HA, so we're using the second column, and our decision here was to reject HO. So rejecting HO, we would say there is enough evidence to support the claim. And there's what we argued intuitively. Okay. Alright, moving on. Get another example, I'm sure. And here write down the givens again on the side. This is always a good way to proceed. And, you could read through the problem, get an idea of the situation, and then go through and pick it apart. Here, a recent study stated that a person smoked, if they smoked, the average number, so an average is their mean, was 14 per day. So that has to do with the claim. The standard deviation of the population is 6, so sigma is 6. The researcher went out and selected 40 smokers. That's the size of the sample, 40. And they found that their average, or their mean number, so that's the mean of the sample, was 16. So that's X bar, because it's the mean of the sample. And so at alpha equaling 0.02, what do we say? And so we should always check to make sure what distribution we're using. We know sigma. Didn't say anything about normally distributed, but n is greater than or equal to 30. So again, use the little flow chart if you need to. It's all based on, do you know sigma? And we do. And just check that one of these characteristics is true. We know normally distributed, or n is bigger than 30, then we use z. So that's our z distribution again. Or the normal distribution. Alright, so now our steps. They talked about the average being 14 per day, but they didn't say anything about the claim in particular. But then down here, if we read on, is the number of cigarettes a person smokes a day actually different than? So different than is suggesting not equal to. Okay, so our hypotheses. First step, state hypotheses, identify the claim. Not equal to, remember HO contains equality, not equal to is not an equality, that goes with HA. So mu is not equal to 14 is the claim. So then we just fill in the complement, mu equals 14 is the null. Alright, second step, standardized test statistic. So again, the formula Z is X bar minus mu over sigma divided by the square root of n. And it's on our formula sheet, as I should have shown you. So plug everything in. X bar was 16. Remember, mu is the hypothesized population mean that deals with the claim. So just look back at step 1. 14 in this case, over sigma, part of the given was 6, and the square root of the sample size n was 40. And so therefore, crunch that down, we get 2.11. Next thing is to find the p-value. First, determine what type of test. Remember, you look at the inequality, NHA. So it's a two-tailed test. So we draw the distribution. Okay, and the p-value is based on the sample statistic. And the sample statistic was 2.11. But we've got two tails going on. Z equals 0 down the middle. You don't even need to really show that, but it's always nice to do so. But this is the z value that's given, or that was calculated, 2.11. The p-value represents the area in both tails. Now to find the area in the right tail, we first have to find the left cumulative area from table 4, which is 0.9826. So that means the area in the right tail is 1 minus that, its complement, or 0.0174. So then our p-value, because it's two-tailed, is 2 times that area. So 2 times 0.0174. So our p-value is 0.0348. Alright, so now we're ready for a decision. And our decision then, step 4, compare p to alpha. P is 0.0348. Alpha was given to be 0.02. P is greater than alpha. And recall that when P is greater than alpha, that means the HO is probably true, so we failed to reject it. So failed to reject HO as our decision, and now our conclusion. Again, use the table or use just intuitive argument. Let me argue it intuitively, then we'll look at the table. HA is the claim. I'm failing to reject HO, which means that HO is probably good. That means HA is not good. And so therefore there's not enough evidence to support that claim. And I'll just say, use the ellipses, you could fill in a nice college-like sentence there. Alright, so we'll stop right there for this video. We'll come back and do a second part, and the second part's going to deal with the critical value method. And so we'll see you when you're ready for that.